Hello, good morning. This is a quick walkthrough on your midterm exam 2 for our 110A on spring 2024. Okay, let's get started. First of all, the true and false. First question reads, entropy is a measure of the probability of a thermodynamic state. Well, so this one is true. We went over this in class. We end up with this general expression that entropy equals to some kind of function of logarithm of probability plus a constant. Right? While the absolute value of entropy doesn't have any real thermodynamic meaning, but it is a measure of the probability of a thermodynamic state. Second question, the Helmholtz energy is minimized in an isolated system at equilibrium with constant temperature and pressure. Well, so this one, I made a mistake in our buffer lecture. So there are two different things that's wrong. First of all, this should be closed system. And secondly, this Helmholtz energy is minimized at constant temperature and volume. But because I made a mistake in our buffer lecture, I'm gonna put both like true and false as correct for this question. Next one, the standard state of pure gas is the state where the gas behaves as an ideal gas at 1 bar pressure. So this one is the tricky question, right? So when we talk about the standard state of a pure gas, there are three different criteria. First of all, it needs to be ideal. And then we have 1 bar pressure, or P naught equals to 1 bar. But it's missing a third term at specified temperature. Now this temperature might be like 298 Kelvin, or it might be some other temperature, but we need to specify it. All right, 1-4. For a closed adiabatic system, so this one is pretty much saying a isolated system, at constant temperature and pressure, entropy is maximized at equilibrium. Right, so basically for material equilibrium in any isolated system, or if you treat the entire universe as an isolated system, entropy is always maximized at equilibrium. 1-5. The condition for chemical reaction equilibrium in a closed system is that the sum of our chemical potential equals to 0. So this is false, right? Note that it's our sum of chemical potential times the Ni, the infinitesimal change of the changes of each like chemical species. Chemical potential is an intensive property. This is true. We went over this in class. 1-7, the chemical potential of 30 grams of liquid water at 100 degrees and 1 atm is larger than the chemical potential of 30 grams of water vapor at 100 degrees and 1 atm. Now note that both of them are at normal boiling point, so we can say that liquid and vapor are in equilibrium with each other, right? So the chemical potential of my liquid form must equal to the chemical potential of my vapor form. So this is true. The term standard state requires that P equals to 1 bar, and that's all right. T equals to 298 Kelvin. So this is false. It can be any kind of temperature. We can specify, say, temperature equals to 273 Kelvin, right? It doesn't need to be any specific. It doesn't need to be like 298 Kelvin as long as we specify temperature is fixed in that standard state that we want. 1-9, the standard state of the element tin is tin white. So this one is reading our thermodynamic table and find out which one is having delta H equals to 0. So let's go to our thermodynamic table here. Well, let's see, where did we put it? Okay, here we go. All right, so when we're looking at tin, we see that there are two different element tin in this table, and we see that tin white has delta H heat of formation equals to 0, and thus that's our standard state for material tin. So this one is true. Last one. So this one is, again, this is a little bit tricky, but think about what is safe to do, right? So what is safe is we can take differential of H plus PV. That always equals to DH plus PdV plus VdP. Right, so if we do the integration, on both ends, what we have, so on the left we end up having delta H plus PV, dH becomes delta H, and then we have the integral of PdV plus integral of VdP. Note that these two are not always necessarily equal to VdP plus PdV. So this one is false. All right, so that's all of our true and false. Next up, short answer problems. So in this problem, the first one reads, given that the normal boiling point, basically it's telling us the boiling point of benzene at 1 atm is 80 degrees Celsius, and asks us to predict the direction of phase change at 120 degrees Celsius. Now, when we have the temperature larger than our normal boiling point, what we expect is irreversible vaporization, or what we have is liquid goes to gas phase or vapor phase for benzene. Right, so remember when we talk about the physical meaning of chemical potential, when we have spontaneous flow of material from one phase to another, the phase where it's going out always have larger chemical potential. Next up, express the temperature dependence of enthalpy H at constant volume in thermodynamic measurables like temperature, volume, pressure, CV, Cp, alpha, and chi. So first of all, what is this question asking about? It's asking us to find out what is the temperature dependence of enthalpy at constant volume, right? So dH over dt at constant volume. Also, what do we know? We know that H equals to U plus PV. And the reason I know to use H equals to U plus PV is we're looking at temperature dependent at constant volume, right? So reading our table, we know that du over dt at constant V, that's something we can measure, that's CV, and hence I'm using the H equals to U plus PV. So my dH over dt at constant volume thus becomes, well, du over dt at constant volume plus here we have PV, right? So again, dPV equals to PdV plus VdP, and in here we have constant volume, so my dV term equals to 0, and then that becomes our volume times partial differential of P over T at constant volume. All right, so what are these terms? First of all, we know that du over dt at constant volume, this equals to CV. Volume is something we can measure. dP over dt at constant V equals to alpha over chi. This you can derive either from the definition of alpha over chi, or we went over this derivation in class together when we talk about the the volume dependence of internal energy. And here we end up having dH over dt at constant V equals to CV plus V alpha over chi. All right. Next up, given the equation of state of a hypothetical gas is pressure times volume minus MB equals to nRT, where B is a constant, ask you to calculate the change of enthalpy of a real gas from the difference between ideal gas and real gas at constant temperature and at constant temperature, T equals to 298 Kelvin, pressure equals to 2 bar. So first, let's write out the equation we want to use, right? So H ideal minus H real. This equals to, from 0 to P naught times temperature times dV over dt at constant P minus V. Right, and then in here we have several things we want to solve. First of all, we want to solve this partial differential. Now, with the equation of state, we can express volume as a function of temperature and pressure equals to nRT over P, and then plus, well, nRT divided by, let's see, NB. Wait, this one is, well, PV minus PNB equals to nRT. So PV equals to nRT plus PNB. So volume equals to nRT over pressure plus NB. Because pressure and pressure cancel out. And we can solve for dV over dt at constant P, that equals to nR over P. And then in here, what do we have? Now in here, taking this all into consideration, we have temperature times nR over P minus volume. Now in here, what do we have? We want to express temperature as a function of pressure because eventually we want to solve this integration, right? So temperature equals to PV minus NB divided by NR, or PV over NR minus B over R. Wait, we have a P here, right? So PV minus NB divided by NR and here we have BP over R. And then plug in this expression for temperature. In here, we get PV equals to NR times NR over P minus BP over R times NR over P minus V, right? So in here we have NR, P cancel out. Here R and R cancel out, P and P cancel out. Well, and here we end up having this term to be V minus V, we also cancel out. So we end up having this entire thing equals to negative MB. So effectively what we're looking for H ideal minus H real equals to integration of 0 to P naught of MB dP, or that's negative MB from 0 to P naught, and since P naught equals to 2 bar from 0, so that's negative 2 MB. Or if you put like negative MB P naught, that's also alright. Alright, next up, 2-4. So here is basically asking you to fill in the graph to make it correct, right? So these are the example we did in class together. And what do we end up having? First one, let's see what are the information we have, and this should be 25 points, by the way. For an isolated system, something is maximized when the system is proceeding towards equilibrium. Now we can first answer like X is at equilibrium, and something is maximized, and that's our entropy. Then for the second graph, right, we see that it's talking about the Gibbs free energy, and it is minimized when we're approaching equilibrium, so that X is prior to equilibrium. And something else is missing, right? We want to have a closed system, constant Tp. Right, so note that, again, I made a mistake in our buffer lecture, so if you put isolated, I also give you credit for it. Next up, now we have our Helmholtz energy. We have isolated system, constant TV, and by the way, this actually gives us the answer to our true and false problem number 2 here. But nevertheless, we're asking you to draw how does my Helmholtz energy change with respect to time. So the kind of graph we're looking for is like this. Right, and now the comprehensive problem. First one, write the formation equation of bicyclobutane. So formation equation basically asks us to write how bicyclobutane is being generated from its elementary form, right? So we want to specify its formating elements from their like fundamental stable elementary form. Or you can check the thermodynamic table to find what is the what's the standard state for those elements. And in here, what do we have? We have 4 carbon, so we want 4 carbon graphite plus 3 H2 gas. That forms C4H6. And note that, what is the phase of bicyclobutane? So we're writing that for knowing that its normal boiling point is 8.3 degrees Celsius. So if we're looking for a like standard state at 298 Kelvin, it should be a gas. And problem number B, you can't really solve it, so I end up just giving everyone the answer to this problem. So the heat of formation of bicyclobutane at 298 Kelvin is 217 kilojoule per mole. All right. Part C, burning of bicyclobutane in oxygen to form carbon dioxide and water in an adiabatic calorimeter. Right, so it's a burning reaction. And it's given that the stoichiometric number of CO2 of this reaction is 8. What is the stoichiometric number of bicyclobutane? This is just write a balanced chemical reaction. So C4H6, which we just write it's a gas, plus 11, plus O2, that goes to CO2 plus H2O. Right, so oxygen is a gas, CO2 is a gas, H2O is a liquid. Now we have 8 in front of CO2, so we must have 2 in front of our bicyclobutane. And that means we must have 6 divided by 2. We must have 6 in front of my H2O. And then on the right, we have 6 oxygen plus 16 oxygen, and then over on the left we must have 11 in front of O2. So the stoichiometric number of bicyclobutane must be a negative number, right? So it's negative for reactant, so that's -2. Part D, estimate the internal energy of the standard internal energy of formation of bicyclobutane. So first of all, we want to find out what equation to use. So in class together, we write out this expression that delta H naught is roughly equals to delta U naught minus the change of number of mole of gases times RT. And in here, what do we have? We have the change of number of mole of gases in the combustion reaction we just write out. In here, we have that equals to -5 more. Right, it's in this question, we're talking about burning of bicyclobutane in an adiabatic calorimeter. So this delta G is referring to the actual reaction taking place in this adiabatic calorimeter. And then it's just plugging numbers. The delta H formation, that's 217 kilojoule per mole, equals to the delta U internal energy of formation plus -5 times RT translate that unit. We can plug it into our calculator to find the internal energy of formation equals to 229 kilojoule per mole. All right, the last one. Last one is given that the heat capacity of the adiabatic bomb calorimeter used is 9,000 joule per Kelvin. We tell you that 5.4 gram of bicyclobutane is combusted at 298 Kelvin. Estimate the delta T of the calorimetry experiment. So this one uses equation of delta F U naught 298 Kelvin equals to negative C K plus P, right? So that's the heat capacity of our adiabatic bomb calorimeter times delta T. So this one is our equation 5.8, by the way. Now this one is just plugging numbers. We have 229 kilojoule per mole. Note that this is for 1 mole of bicyclobutane burned, equals to -9 kilojoule per Kelvin delta T. Right, so we end up for every mole of bicyclobutane burned, the change of temperature must be negative 229 over 9 equals to negative 25.4 Kelvin per mole. Right, so we can calculate the number of mole of bicyclobutane. That's equal to 5.4 gram times 48 gram, 48 plus 6 gram per mole. That equals to 0.1 mole. So my delta T must equal to negative 2.54 Kelvin. Note that if you calculated this internal energy of formation to be something wrong, but you did all these calculations correct, you're supposed to get full credit for this question for consistent result. If we graded wrong, just remind us by submitting a regrade request. All right, that's all from me for our midterm 2 walkthrough.